So outlining is fairly used optimization for size, code size. It's basically finding these repeated instruction sequences and outlining these sequences, and then replacing the original sequences with a jump call. For example, in these one func and two func, you can see that same set of instructions are repeated. So what you do is you basically extract them into a different function, and then at the original call sets, you just replace it with a jump to this newly outlined function. So what I'm here to talk about is differential outlining, which is while we looked at same set of instructions in outlining, here we want to look at similar sequence of instructions rather than the same sequence of instructions. Here, we would again then outline the same sequence of instructions with generics while replacing the differences between the sequences. And then at the original sequence, you basically replace it with a jump to the outlined sequence, but also account for the differences. Now there are various different possibilities that can come out because of the different kinds of differences that can arise. For example, in 3 func and 4 func, you can see that these two sequences just differ by a constant. And so what you do is you outline the sequence with replacing the constant with a register as shown. And then you basically move the immediate or the constant into the register, and then you call the outline. So to put out what is the differences between outlining versus differential outlining, first we saw in outlining we look at same sequences, whereas in differential outlining we look at similar sequences, and then the similarity could be of different types. It can give rise to different kind of differences between the sequences. And then you cannot use normal hashing for similar sequences, because if you hash, then even a slight difference can give you a different hash. And then while outlining, in differential outlining, you have to take care of the differences that are between the sequences while outlining it. So broadly, for our purposes, we classify the different kinds of differences that can arise into 4 types. One is instruction differential, where one sequence is strictly subset of the other. That is, one sequence has few more instructions than the other sequence. But the subset instructions are actually present in the superset. And then there is register or immediate differential, where the instruction sets are the same, the opcodes are the same, but they differ by register or immediates or constants. And then you can have instruction and register differential. Basically, you can have instruction sequences which differ by, where one is the subset of the other, and also it differs by register or immediates. And then you can have all other kinds of differences, which we call unsubsumed differential, where one instruction sequence can completely deviate from the other sequence. So now, how do we find these similar sequences? Because comparing instructions in the sequences is not scalable. And then these sequences, it need not be the same size. So they can match at different positions. So what we do here is we come up with a similarity preserving encoding, where the hash of two set of sequences is close enough, or the Hamming distance is close enough if they are very similar. And then what we do is we use this encoding to cluster these similar sequences using the encoding, basically to account for the scale. And then once we have the cluster, we can only compare the candidates within the cluster to get these similar instruction sequences. So for similarity preserving encoding, we developed an algorithm which is based on MSRH-v2, which is a similarity preserving hash. What it does is it uses Bloom filters, and it takes chunks of data and different hash functions, and you basically set the bits in the Bloom filter based on these hash functions for those chunks. So and what you get is basically you get two encodings, and the difference in the bits of the encoding actually gives you the similarity metric, how similar two particular sequences are. And for our cases, we want the order of instructions to be right, because we cannot, even if the instructions are same and the order is not same, we cannot outline these sequences. And then we also prioritize the instructions are similar if they have the same opcodes, because if the instructions differ with register and constants, we can outline these sequences. For example, here in function A and function B, these sequences only differ by the constant and the jump address at the last instruction. So they have similar encodings and they differ by a couple of bits. And then we do clustering, where we use, since we know that the closer the more the number of bits that are common in these encodings, the more closer the similarity is. We use locality sensitive hashing, where we use banding and basically divide the encoding into different parts, and then try to match at least one of these bands or these divisions. For example, in the same sequence, function A and function B, we divide the encoding into 3 parts, and we see that one of the bands match. So if at least one of these bands match, then it's a possible candidate for having similar instructions. And we can then move on to comparing it by instruction by instruction. So now now we can find different all the possible similar sequences by scale, and how do we handle it? So in case of instruction differential, where one sequence is completely subset of the other, what we saw was with outlining enabled, this basically transforms to consecutive outline calls. For example, here you have one func and two func, where your outlining has already transformed these separate instructions into different outline calls. So all we have to do is basically take these outline and run another outlining pass on top of it, so that we outline these functions. So we basically do that, where we take these two consecutive outline sequences and then outline this into a different function, and then call that outline function. So this gives us around 2 to 3% code size savings on our social media app. And then what we do with register and immediate differential, we saw that if we apply this at function level, then this problem transforms to finding similar functions rather than similar instruction sequence, and we can do function merging. So just using clustering on top of similarity preserving hashing saved us around reduced the overhead by 48 times. So we are able to find all the similar functions within our social media app very quickly. And then what we plan to do is we basically replace these constants with registers, and then also we can replace the jump addresses with registers, and we can outline these functions. And we are currently implementing this in the linker. And then this can be further extended as part of future work to any sequence that and need not be part of, it need not be at function level, but can be any set of instruction sequences using the same similarity preserving hashing and clustering to reduce the overhead. So that's pretty much it. The main takeaway is basically the new way of finding these similar sequences at scale using the encoding and clustering, which is kind of inspired by the natural language processing algorithms, And this can help us discover new opportunities in code side reduction and other use cases. Thank you.
Thank you, Girish.